Assuming complete dissociation, what is the pH of a 4.18 milligram per liter barium hydroxide solution? So the first thing we need to do is figure out how is barium hydroxide going to impact the pH when it dissolves. So let's look at what happens when it dissolves, and I'll go ahead and we'll put a solid state there. All ionic compounds are solid at room temperature. When barium hydroxide dissolves, and again we're assuming complete dissociation, we form the barium cation and 2 moles of hydroxide per mole of barium hydroxide. And so this is going to be what is going to impact the pH. Now sometimes cations can impact the pH, but if we look at the conjugate acid of a strong base, these cations never impact the pH. So the only thing we need to figure out is the concentration of hydroxide. Once we figure out the concentration of hydroxide, then we can figure out the pOH, and once we know the pOH, we can easily calculate the pH, since pH plus pOH is equal to 14. So since we need a concentration of hydroxide, the first thing I want to do is change my mass to moles. I'm given 4.18 milligrams per liter, and so I want to change my milligrams to grams. So I multiply by this conversion factor. 1 times 10 to the minus 3 grams is 1 milligram. My milligrams cancel out. Once I'm in units of grams, I want to convert to moles using the conversion factor of molar mass. 171.34 grams of barium hydroxide is equal to 1 mole of barium hydroxide. So my grams cancel out, and then I went ahead and canceled out this barium hydroxide as well. So at this point of my math, my units are moles of barium hydroxide per liter. My liter has remained. I have not changed that at all. But I don't want moles of barium hydroxide. I want moles of hydroxide. So to get to moles of hydroxide from moles of barium hydroxide, I use the chemical formula. For every mole of barium hydroxide, there are 2 moles of hydroxide that dissolve. So all of my units cancel out except for moles of hydroxide per liter, and moles per liter is concentration, and we use this shortcut abbreviation for concentration of molarity by using the brackets. So the concentration of hydroxide is 5.614 times 10 to the minus 5 moles per liter of molarity. And I got that by multiplying 4.81 by 1 times 10 to the minus 3, dividing by 171.34, and then multiplying by 2. And of course these 1's in the denominator and numerator will not impact the overall value, since anytime you multiply by 1 or divide by 1, it doesn't impact the overall answer. Now that I have my concentration of hydroxide, now I can figure out my pOH. The pOH is going to be the negative log of the concentration of hydroxide. And according to the calculator, that's 4.25. Now I realized when I was recording this that I was a little careless with my significant figures. This value, even though there are 3 digits, only has 2 significant figures. With pHs, it is the value after the decimal point, or to the right of the decimal point, that are considered significant. But I think sapling is okay with just 2 digits after that decimal point. I don't think it's going to be that careful about significant figures for these problems. So, back to calculating the pH. We know that pH plus pOH is equal to 14, and so if I isolate pH by subtracting pOH from both sides of the equation, I get 14 minus pOH is equal to pH. So the pH is 14 minus 4.25, which is 9.75. And this makes sense because this is a pH that is greater than 7, which means the concentration of hydroxide is greater than that of hydronium. And that's what we would expect when we dissolve an alkaline earth hydroxide, that it would be a basic solution. So our final answer makes sense.